Hello. We will go over the concept of limits and continuity for functions of several variables in this lesson. And we're not going to spend a lot of time on this topic, and you'll see the reason why as we move along with this material. I just basically need to go over enough of the concepts of limit and continuity so we can quickly move to the definition of partial derivatives, which is the more important part of this chapter. The reason we don't spend so much time, you'll see, is because some aspects are far more trickier than in Calculus 1, but the main idea is really the same. So I'm basically assuming that you understand the overall notion of a limit, even if you didn't study the rigorous definition and properties of a limit, like with epsilon and delta definitions. I'm not going to get into that either. So we're going to just give a very intuitive definition of, descriptive definition of a limit. But even if you remember just that, it's important to point out that kind of the same concept works for functions of several variables as well, with an important caveat, as you'll see in a moment. But let's just recall from Calculus 1 that if you have a function of a single variable, you say that the limit of that function as x goes to x naught is some quantity L, which could be a number or infinity or minus infinity. Let's just say it's a number. I mean, usually for infinity or minus infinity, we have slightly different definitions. So we say that this limit is L if we can make f of x as close to L as we want by making x as close to x naught from both sides. And the last part actually is important, and it's the devil in the details, so to speak, when we get to functions of several variables. So I want to encapsulate in this brief description all of the caveats with the limits of a function of a single variable, right? So the idea is that, if you look at the graph of a function like that, and this, the way I drew it here, it's actually a continuous function. We'll get to that in a moment, right? So if the function is continuous, then the limit is just a matter of evaluating the function at that point. So the idea is that so this is the graph of the function f of x, right? So if I take a point x and I approach x naught from both sides of x naught, right? Does the corresponding value of y approaches the actual limit L, right? From both directions. So that is because the domain is made by a single variable, meaning that on the real axis, right? So if I have the point for which x is taking the limit to, right, x naught, the only way to approach the point on the real axis is from either left or the right hand side. Okay, so for example, if I pick values from the left side, you could remember the convention of notation in that case is to look at the left-sided limit, right? So one convention of notation was to say x approaches x naught with a minus sign to indicate that you approach the point from the left side. And then if you approach it from the right-hand side, then the convention of notation was with x approaches x naught plus, and that will be the right-sided limit. And of course, this limit may exist, or one of them may exist, the other may not exist, or both can exist but not be equal to each other. So remember from Calculus 1, we got into those properties in which we studied under what conditions, for example, a function may not have a limit. When it does have a limit, of course, it's kind of easy to visualize, especially if it's a continuous function. But also the way in which a function may not have a limit, there's just a handful of ways for that to happen in the case of a function of a single variable. So for example, if the sided limits are not equal, right? So if you have something like that, let's say you're looking at the limit at x naught, but as you approach it from the left side, you get some number L1. As you approach it from the right hand side, you get a different number L2. So in that case, the limit may not exist. The limit at x naught does not exist. Furthermore, continuity for a function of single variable, remember the definition of that concept simply states that for a function to be continuous at a point, first of all, the function must be defined at that point. Remember, a limit may exist even if the function is not even defined at x naught, right? So the notion of a limit doesn't require the function to be actually defined at the point x naught. But for continuity, you need it to be defined, and moreover, the limit itself should be f of x naught. So this equality essentially states that f is continuous at the point x naught. So that's the reason why in calculus 1, and even if you don't remember this entire discussion, if someone says, okay, find the limit as x goes to 3 of x squared minus x, let's say, right? And then you plug in 3, you notice that nothing spectacular happens, like there's no undeterminate case, there is no fancy method that you need to use to evaluate the limit, like a L'Hopital rule or rearrangement of the terms. You simply plug in the point for which x approaches to, and you get the number, and then you say, okay, that's the limit. But that's essentially, in a way, verifying the continuity and using it at the same time, basically, to find that limit. And I want to emphasize that this continuity property holds also for functions of several variables. And moreover, another crucial property for limits, the composition of continuous functions is continuous, which is the reason why, for example, once you prove that, let's say, the power function next to the n is continuous, you don't have to prove that a polynomial is continuous, because a polynomial is a composition of power functions and so on and so forth. But again, hold this thought in your mind, the fact that non-existence of limits in calculus 1 for a function of a single variable, it can be tricky in that case as well, but there are not that many ways in which that can happen. I mean, of course, problems to show that a limit doesn't exist can be a hard problem even in calculus 1. But it can be particularly difficult in calculus 2, which is the reason we don't delve into that too much. We studied the limit for the purpose primarily to introduce the derivative, and then nearly all the functions we're going to encounter for the topics we're going to learn in calculus 3 will be continuous. So we won't have to worry about that. But it's important to know the difference between calculus 1 and 3 when it comes to the concept of a limit. So let's move on now to the definition of a limit. Again, I'm going to use the same intuitive definition for functions of several variables. We're going to say that limit, so we say that, let's state this for a function of 3 variables, same idea works for a 2-variable function. So we say that the limit as x, y, z approaching x naught, y naught, z naught of some function f of x, y, z is some number L. If we're going to just restate the same property, right? If we can make f of x, y, z as close to L as we want, by making x, y, z close to x naught, y naught, z naught from any direction. And notice the key word here that I'm using here. Instead of saying left or right, I'm saying that we need to have this property to hold as x, y, z approaches x naught, y naught, z naught from any direction. We're going to talk about that in a moment, what this distinction means. And the definition for a function of 2 variables, for the limit of a function of 2 variables, is going to basically be analogous, right? So let's establish from the beginning that if the function is continuous, I mean, we say that the function is continuous, just like in calculus 1, if the limit I'm going to, just to not waste too much paper, I'm going to state this for a function of two variables. The same thing works for a function of three variables. So if the limit of this function happens to be the value of the function evaluated at that point, so of course f needs to be defined at x naught, y naught, we're going to say that f is continuous at the point x naught, y naught. And as it turns out, again, the composition of continuous functions is itself continuous, which is the reason, and let's start with this example, which is the reason why, just pretty much just like in calculus 1, if you plug in the point for which the limit is computed, right, like 1, 2 in this case, into the function, let's choose actually a polynomial type function here, a polynomial in two variables this time, right? X squared y, let's say minus y x fourth. So plug in 1, 2 for x, y, right? That means x is 1, y is 2. By themselves, x squared, y x fourth are actually functions of a single variable. So we know they're continuous from calculus 1 and viewed as functions in calculus 3, right? I mean, in 3D. The composition of them is also continuous. So therefore, this is, in this case, is 0. Therefore, the limit is going to be 0 by simply evaluating the function at 1, 2. Here's another example for a function of three variables. Let's say I take x, y, z to approach the point 1, 1, 1. Evaluate for the function x, y, z divided by x squared plus y squared plus z squared. Just plug in 1, 1, 1 for x, y, and z. Again, nothing really fancy. The limit is going to be 1 over 3. So, before we move on to the next page, I'm going to spend the rest of the class today to explain essentially what are the tricky problems in which it's not that easy to figure out if the limit exists, and if it does exist, how to compute it, and how to prove that it doesn't exist if you suspect that the limit doesn't exist. For my class, so those of you who are my students watching this, I don't usually evaluate, I don't evaluate in the exams these questions, these non-standard ways of, or non-obvious ways of proving that the limit doesn't exist, or proving that the limit exists and how to find it. Again, when it's not obvious how to do it. So I don't actually test this. But for the homework at least, or maybe a quiz, I think it's important, if you go through calculus 3, to know at least one example of each. One example in which the limit exists, but it's not easy to compute it. So in other words, the function is not continuous, yet the limit exists, and how to find it. And another example for which the limit doesn't exist. I think it's worthwhile to actually know at least one example of each. So we're going to spend some time with this on the next page. All right, so let's begin with the following example. Let's say I want to compute the limit as x, y approaches 0, 0, so a function of two variables, of the function x, y fourth divided by x fourth plus y fourth. All right, so the bad news is that there is no standard way of actually dealing with problems like this. So let's establish a remark here. Clearly, the function is not continuous at 0, 0, because it's not even defined at 0, 0, right? So you cannot plug in the point 0, 0 into the denominator, right? And it's going to be over 0, so that's not defined. There is no standard way of actually deciding whether the limit exists and what it is, or how to prove it doesn't exist if you think it doesn't exist. You kind of have to figure out, maybe with estimations and plugging in some values close to 0, 0. You got to have an educated guess on whether actually the limit may exist or not, and actually guess the value of it. Now, of course, if you do some typical examples like this, often these examples are kind of similar to each other. You kind of learn the trick of the trade. So for instance, if you look at this quantity separately, you may notice that in fact it's going to be always between 0 and 1, because x fourth, y fourth are all positive numbers. The bottom is bigger than the top, so that should be probably that's going to be between 0 and 1. The reason that's important is because that gives you two clues. One of them is that probably the limit is 0, because you have basically a fraction less than 1, roughly speaking, which is multiplied by another x, which by itself goes to 0. And then you may think about how to prove that the limit is 0 by using the so-called squeeze lemma from calculus 1, which still holds in calculus 3, by the way. Squeeze lemma, remember, is when you can manage to bound your function between two other functions. Again, that lemma still holds, or the squeeze theorem still holds for calculus 3. Potentially simpler functions to evaluate. So if the two bounding functions converge to the same limit, that proves that the original function converges to that limit as well. I should also mention that it's not like in calculus 1 when you actually can look at whether you approach 0 from the left or right. So, and see, this is the main difference. As I said before, pay attention to the wording. The limit should exist as x, y approaches 0, 0 from all directions. In calculus 1, like I said, you approach the point for which you compute the limit either from the left or from the right. But right here, the domain of the function, in this case at least, is the entire region in the xy plane. That's the domain. Okay, so then the point 0, 0, in how many directions can you approach 0, 0? Let's actually use a different color so I won't confuse it with my markers here for the actual domain. Well, notice that you can approach 0, 0 just like in calculus 1 from left and right. That is to say, it's like you keep y 0 and then you approach x from negative values and then from positive values. Or you can approach 0 over the y-axis. Or you can approach 0 from diagonal. Or you can approach 0 from some winding path like that. So in other words, there are infinitely many ways to approach the limit point, to approach 0, 0. And the problem is that if the limit doesn't exist, you may have various actual limits, different limits for different paths. So the equivalent, we can write it here in words, the equivalent of distinct sided limits, left and right, in calculus 1, in calculus 3 is equivalent to distinct, potentially distinct limits for different paths to the limit point, x naught, y naught, or 0, 0 in this case. So that's what makes it hard, in fact, to show that the limit doesn't exist if you think the limit doesn't exist. Because, for example, let's say you check 2, 3 different directions of approaching 0, 0, and you say, okay, I got this limit in all 3 cases. There can always be another fancier weird path winding out like that may give you actually a different limit, which essentially proves that the overall limit may not exist. You'll see that in my last example. Now, the example here that I started the page with, this one turns out it does have a limit and it's actually 0. Now, how do you prove that the limit is 0? Because you cannot plug in 0, 0. Like I said, usually the squeeze lemma works as soon as you actually kind of suspect what the limit is, which I said that you kind of can kind of tell that the limit is in fact 0. So how do you do that? Well, you can take the absolute value. I'm bypassing actually one of the properties. Basically, if the absolute value goes to 0, then the original one goes to 0 as well. So the absolute value of anything is going to be greater than or equal to 0. And I'm going to use some properties of the absolute values on the right hand side, and I'm going to distribute the absolute value to x times the absolute value to y fourth over x fourth plus y fourth. Now remember, when xy approaches 0, 0, you approach that point but never actually equal to that point. So as long as not both x and y are 0, this quantity right here is always less than or equal to 1. Okay, which means that this quantity is going to be less than or equal to absolute value of x. But now, what is the limit of absolute value of x as xy approaches 0, 0? Now notice, now this becomes a calculus 1 question. Because as it happens, the bounding function to the right-hand side doesn't depend on y anymore. So y is relevant. So it's just me asking essentially what the limit of absolute value of x is if x goes to 0. And we know from calculus 1 that x goes to 0. Since both bounding functions approach 0, we conclude that the middle one goes to 0, which is to say the original one, the original function goes to 0 as well. These are the typical tactics one can do with a squeeze lemma for functions of several variables. Ideally, you have these bounding functions that depend on a single variable, so you basically switch the problem to a calculus 1 question. Okay, here's my last example. What if I want to compute the limit of xy approaching 0, 0 for the function xy divided by x squared plus y squared? Now, a clue that the limit may not exist in this case. First of all, again, notice it's not continuous at 0, 0, so I cannot plug in 0, 0. But a clue that it may not exist actually is to look at the degree of these polynomials. If you look previously, the degree on the top was 5 if you add the powers, right? X, y to the fourth, that's going to be 5 over x fourth. So it's kind of analogous to, in calculus 1, let's say, to the limit as x fifth over x fourth, right? Roughly speaking, right? So it means like, we know x goes to 0 if x approaches 0. Now here, when the powers are when the degrees are the same, 2 over 2, unlike calculus 1, this is a typical sign that the limit doesn't exist, because you could always find different paths that converge to different limits. That is like a different situation, because in calculus 1, you remember if the degrees on the top were equal, I'm going to make a little short detour here. If you had, for example, let's say, well, I guess it depends on the function, but well, yeah. I'll take it back, because even in calculus 1, you could have examples in which it may or may not exist depending on the situation. But here, what do I mean by different paths with different limits? So let's look at the domain again, which is the entire real number. The entire 2D plane. And this is the point for which we compute the limit. So first of all, there are plenty of paths of approaching 0, 0 for which the limit is actually 0. So let's say, for example, I'm going to approach, let's use again the green color. Let's say I'm approaching the limit point with values from the x-axis, from the positive semi-axis. Like for example, 4, 0, 2, 0, 0.10, so on and so forth, right? So I'm approaching 0, 0 with points on the x-axis. So that means y is 0, x approaches 0, but not exactly equal to 0. So that means on this path, the actual function is going to be x times 0 over x squared plus 0 squared. If we simplify this, that's going to be xy over x squared. Yeah, actually it's going to be not... x goes to 0. Sorry, yeah, I mean I got sidetracked by something. So on the top is just 0, right? Because it's x times 0. Y is fixed at 0. And then on the bottom you have x squared. Again, that's going to be 0. So basically that's going to be the constant function 0. I got confused by something else. I looked at my notes. So again, if you approach 0, 0 on this path, on the x-axis, the function is the constant function 0 because y is going to be 0. So the limit on this path is 0. Okay, but what if we approach, for example, the 0, 0, let's say, on the diagonal path? Again, these are classical textbook examples, and you will see probably this problem in most of the textbooks. And there are variations of this in the homework, as you will see. How do you characterize the points on the diagonal that approach 0, 0? Well, those are the points for which x is equal to y, right? So if x is equal to y, what does the function become? The function becomes x times x over x squared plus y squared, plus x squared, sorry. That simplifies to x squared over 2x squared. That simplifies to 1/2. So on the diagonal path, the limit is 1/2. 1/2 is not equal to 0. We found two paths for which the limit is distinct. It depends on the path, in other words. That means the original limit of the original function does not exist. But I mean, I'm going to conclude the lesson with this remark. You can see how the concept of proving that the limit may not exist could be extremely tricky, right? Because the function could be so difficult and so complicated that those two paths that will give you different limits may not be easy to find. There might be lots of them that will give you a certain limit, like 0, but there might still be a pesky, weird path that gives you a different limit, and unless you find it, then you won't know for sure whether the limit exists or not. So anyway, with this in mind, we're going to move on, and we're going to spend far longer time, definitely a longer time on the next topic, which is the introduction to derivatives of functions of several variables, namely the partial derivatives. So we'll get to that next time. See you later.